Good evening all. So today is our last class. Today what I am going to do is I am going to give you the whole actually summary that we have learned in this course, and it I would try to explain briefly the every important topic, and then if you have any question you can ask. Uh, that's why today we are going to discuss. Initially, when we have started, the initial, the major learning part was that Ziegler-Natta catalyst and this particular reaction for polymerization. So, if we look into the mechanism, obviously there this particular reaction was discovered by Carl Ziegler and Guido Naka. They are actually these two transition metals like titanium, zirconium, hafnium. In these blue quartz metals, they are actually used in this particular reaction. If you look into the uh, that's two metals or two reagents that are used are like this way. KiCl4 and ETCL, so this is first Louis acid and this is the metal part we should do the metal. So another variant was TiCl3 and AlETCl. So these two combinations are used for this kind of reaction. Initially when this kind of alkene was treated with this catalyst, so that then linear polymerization chain formation was observed by them and their molecular weight that they are achieving in this particular condition is much more than then available method like mainly radical and cationic polymerization. So their branching was there and molecular weight of that polymer was not also very much good or great. So with these things, they have able to make that linear polymer with high molecular weight polymer. So that's one of the key discoveries in particular field. These are two actually two variants. If they want to stochasticity obviously hybrid. If they want to make this kind of isotactic polypropylene, uh, then these two combination are used, and when they want to make kind of thinner tactic polymers, so then vanadium based reagent were used. That variation would lead to different products. This is the radical based mechanism. So initially radical was generated. This is one of the key actually methods for synthesizing this kind of polymer. Uh, this is actually the which have advantage of that this kind of polymerization always leads to low molecular weight polymers, and obviously branching is very much visible. So when they want to, or they did with this kind of transition metal, so there we can see how this kind of orbital interaction happens. So DXY and pi bonding. So this is your resin and this is metal. So this kind of interaction is there, and this is uh, the bond formation, and this is back donation. So both properties are there. And so this is the initial orbital interaction, how that alkene and your titanium react with each other. Initially titanium was activated with this kind of Lewis acid. So one of the uh, uh, fluoro group is kind of shifted or reacted with aluminum or trapped, you can say trapped by aluminum, so that one active site is generated like this, and this particular center is free, and it can react with your alkene. So here it is shown like this thing. This particular active site is now reacting with that alkene part with the help of this kind of orbital interaction. When it reacts with that, so you can expect formation of this kind of four-member transition state and followed by this kind of shift. So that would lead to titanium carbon bond formation, and this particular bond would be flipped. So this particular ethylene group is now attached to that polymer ring, or that alkyl ring, you can say. So with variation of this particular aluminum-based reagent, so here it can be methyl, ethyl, this kind of things. So with variating this, you can expect formation of different polymeric chains. So that's a way to make different kind of polymers. And according to your design, what you are making, you can do that. So this is initial reaction. After that, this particular thing happens. So now again you can see that active site is regenerated in titanium, and this can react with your second equivalent, or the other equivalent of your monomer units, and that's way to grow that polymeric chain. And this particular step can repeat, and it can give you high molecular weight polymer. For termination step or termination approach, there are a few. Here you can see that this kind of titanium hydride formation can be possible, and that would generate an alkene unit in the end of your polymeric chain. So this is one of the way how that this particular reaction can be terminated. And this is another possibility, you can say, that this particular titanium and hydrogen, so it's kind of agonistic effect. So if this is not happening, then this kind of transition state is possible. So here the titanium is reacting with another monomeric unit. So this is the alkene that you can see. So this kind of interaction can be there. Now this hydrogen can react with this particular center, or this carbon, which would ultimately lead to the formation of this thing. So this is the end group you can see, and that titanium would be left as this kind of isopropyl group that can be attached with titanium. Yes. This is one of the ways to terminate your polymerization reaction. And lastly, this is another way. So if you do that hydrogenation, so that hydrogen can also react with this, and this titanium carbon bond can be broken. And this is another way to terminate your polymer formation rate. So now the for this kind of propene polymerization, this kind of Grignard-Lassa catalysts are highly reduced, and they favor formation of this kind of one-two primary insertion. So here you are seeing that this metal center try to be in the end end of that group, or where the bulkiness is very much low. So due to that reason, this is quite selective, and this one two insertion is leads to this kind of uh, intermediate, and that's why you always get that linear kind of chain growth. So this is the primary insertion. So that's actually the reason why you always have this regius selective product. Now coming to the transition state. So if you remember, so here when this alkene and titanium, they are reacting with each other, so this kind of full member transition state are forming. So it is a 2D representation. But if we imagine it in 3D kind of conformation, here we can find see that there are quite few options of that stereochemistry. So with this, actually, we can explain that syntactic, or So that's the way we can express two formation of these two variants actually. In the textbook for that isotoxic polymer. So, so that's the way we can control that similar toxicity or isotoxicity. So that's the way to explain because when you have this kind of condition state, you can see after polymerization is to methyl, their orientation would be in the same state. So they are actually above or below, but the point is they are thin to each other. And here you can expect to have a this kind of sigma plane. So they are actually meso compounds or meso diads is what it is called actually. Meso diads can be formed, and it's the transition state for that. And for this kind of cases, you should expect formation of the polymer where methyl, they are kind of this kind of way. So there you can say they are kind of racemic. So they are actually racemic diads. So that's the difference between these two transition state, and that would lead to this kind of racemic diet or mesodiet. Now, so that is what here it is shown here like this. So for this kind of trans geometry, you can expect formation of this kind of racemic diet and this kind of syntactic polymer. And for this kind of case, it will be through this. Now the question is how this kind of titanium or vanadium they are affecting this kind of selectivity, whether it is syntactic or isotactic. So for here you can see that when you use this kind of metal, so depending upon this, Y means that the ligand what is attached with your uh, metal that can dictate between this kind of selectivity. Because for this case here you can see it is a isobutyl group. So isobutyl in this way it is a isobutyl group, and for this case it is a ethyl group. So obviously, isobutyl's bulkiness is much more higher compared to your ethyl, this kind of ligand. So what happens is for this particular case that this methyl and this methyl, this interaction is much more prominent compared to your methyl-ethyl interaction. But when you have this bulky isobutyl group, this isobutyl and methyl, this particular repulsion predominates. And then system tries to minimize that. And uh, for this kind of cases, this methyl-methyl interaction is much more lesser compared to this methyl and isobutyl group. So that's why this particular orientation changes. So we want to write so here this methyl interaction is lesser compared to methyl and isobutyl interaction. Isobutyl. And for this kind of cases, methyl interaction predominate compared to this methyl ethyl interaction. So that's the way to decide between this kind of selectivity, whether it should be isotoxic or indirectly. And the uh, uh, way you can decide this particular this. So comparing this particular ligand, you can decide whether which pathway you should choose. Now this is the way to decide that your this kind of toxicity dependence. Now, when you want to measure this So, so this is the theoretical part. Now, experimentally, when we want to characterize that, so when we want to characterize this, so we actually use NMR technique itself, we can do that. So, this is the general formula for that. So let's see how this particular n can be calculated. So if you want to know how much monomer units are attached with each other, so this kind of technique is very much useful. So let's say you have this kind of polymer. So where that n group is this methyl. So it should come at this kind of 3.4. So this is for this particular methyl. Now, if you here you have four hydrogen, and that would be your repeating unit for this kind of polymer. So, comparing these two ratio, we can actually calculate how much monomer units are attached and make that particular polymer. So, in this particular reaction or polymeric samples, they this for with four hydrogens they got here 165. This is the integration they have got. Now this is the general formula how to measure that degree of polymerization. So that is given by this particular ratio Mn and M0. So mean that weight average and number average. That's two ratio. Now this can be determined by this. So this is the general formula, and with this we can actually calculate this kind of polymerization. So the whole calculation. So here we have solved. So let me just go there and see here. So here actually we have solved everything. So this. So if we apply over here, so here you can see integral of that repeating unit, so 155, and number of photons of the repeating unit is 4, and number of photons in the n50, and what is the integration of that? It is 2.7. Now, if we want to calculate it, we can just do this simple calculation, and from here we can measure that repeating unit or that value of n. So, if we divide, it would be at this point this, and with this can do that. Mm, It should come around 46. So this is the repetition unit or area. Now we can then we can calculate this kind of things because we have now this particular number. So in that way, actually, help of NMR degree of polymerization can be measured, and this technique actually is used for this kind of measurement. Now, after that, let's we have actually at that plasticity. Now, if we see that three major variants that we have learned was isotoxic polymer. So for here, every diet. So, so how to determine that? So in this particular case, here you can see this kind of two pure centers are there, and they can be separate. And actually, this is the way to decide. So here you can see that here you have mirror plane of sigma, and then here you have sigma. Here also you have sigma. So they are actually compound, meso diads there you can say because we are comparing between these two countries only. So they are compared into like this. So for isotactic macromolecules, they are always content of 100% mesodiads. So if you have this chain and you can observe this uh, a particular relation, then only you can say that they are isotactic polymers. Now, how to decide that before? So then with NMR only you can decide this kind of thing because it can be decided with help of these two hydrogens. So for this kind of mesodiads, this hydrogen is closer to this R group and this R group. But for this hydrogen, they are actually far away. Like so, the relationship between these two hydrogens, so we can say they are not chemically equivalent. So when in the NMR, there you can see kind of doublet formation you are going to see because they are diastereomeric compound because they are chemically non-equivalent. So for this kind of isotactic polymer, you can for this pH2 group, you can see this kind of two peaks or doublet. Now coming to syntactic polymer. So for here, 100% racemic diet would be there will be 100% racemic. So again, the way to decide is this stereo center. So always try to find this diet means two adjacent stereo center. So for this case, here you can see if it is R, it will be A. So their relation is racemic. So that's why they are called this racemic diet. Now, if we compare that protons, so here again you have this proton and this proton and this proton. Now, here you can see this proton is closer to this R and far away from this particular R group. And this hydrogen also quite thin because it is now closer with this and far away from that. So in that way, they actually balanced and they are actually now chemically equivalent. So they are not chemically different. So in the NMR, you can expect having one system. So as they are not basotropic protons, they are homotropic protons. So there you are going to get one signal like for these two protons. So for this is the way to decide. So for isotactic polymers, you are going to have a doublet for this CH2. For syndiatactic, you are going to have this singlet for this particular two hydrogen. So in that way, you can decide whether it is isotactic or it is a syndiatactic. Now coming to the property. So for this isotactic polymer, they are actually semi-crystalline and often form a helix conformation. And for the syndiatactic polymers, mm, they are it is actually crystalline and they are generally made by metal resin catalyst. So that's kind of sandwich molecules we have read. So with the help of this that kind of catalyst, generally these syntactic polymers are made. And for atactic polymers, what we can say is, and it is actually disordered, means there is no such the order in this particular arrangement. So if we now see the diads, again with the diad only we can see. So this diad is meso, or this diad is racemic. And again it is this meso, and again it is racemic diad. So there is no such order in this particular arrangement. So where you have this percentage of mesodiads is between 1 to 99% means some amount of error is there, then we call it as a tactic polymer. So for this kind of cases, you would see no such pattern. And when these kind of patterns are missing, then we call that kind of chain or polymer system as ataxic polymer. Now coming to polypropylene, and there are several classes, and with that we can decide. So ataxic, syntactic, isotopic that we have just read. Now for polypropylene, if we see, so the ataxic polymers, they are actually amorphous in nature. So with this only we can so with this macroscopic property ultimately leads to the what kind of property that is going to show by that your material that you are preparing. So that's why this kind of symmetry arrangements and deciding which kind of polymer you want to make that actually depends on this kind of thing. So now for ataxic, they are amorphous, and for synaptic, they are semi-crystalline. And here you can see the melting point. They are also, which is very much differing. So for synaptic, it is 160, and for isotactic, they are 180. So in that way, according to your obviously need, what you are going to prepare, you can differentiate that catalyst that you are going to use, and you can make kind of something. Yes. Now, coming to the mechanism of polymerization. So, various mechanism we have read for among them. This one of the ones. So, this is called as step growth polymerization. So, generally for directly radical based or cationic anionic based, it's for this kind of polymerization. But step growth polymerization, because initially it's kind of two monomer units are attached to each other and randomly, and followed by they actually grow. So now this link is formed, this link is formed. In that way, they actually grow in step by step manner. So that's why this kind of mechanism is called step growth polymerization. So these are the examples of that. So generally with that uh, condensation or this kind of amide bond formation for this kind of mechanism, they goes to this step goes polymerization. So here, let's say you have this kind of system where this X is any kind of halogens and Y is this kind of people. And when they reacted with this kind of nucleophiles, namely, let's say is kind of O minus kind of actually nucleophiles that are used. So that additional elimination reaction will take place in this kind of aromatic system, and in that way, that's your cell can grow. So this would go via this kind of step growth polymerization. So this is the example of that. And for this amide formation also, you can expect the same thing, because now this amide would react with this kind of anhydride, and in that way, this thing will be forming. And here you can see that amide bonds that is formed like this. Now, step by step manner it will grow, and ultimately this condensation would be to this kind of case. And the main key reaction is that amide bond formation, and they go via this kind of mechanism. So this is the examples of these both polymerizations. So there are different classes comparing to monomers that you are using. So in particular, the type what we are seeing was A2B2 type, because had the acceptor or acidic part, you can say. So for here, two acidic parts are or acceptor parts are there, and and that base that you are using, that is having also two nucleophilic units. So that's why it is called A2B2. Now for this kind of cases, you are seeing it have three carboxylic acid groups. So that's why here you can expect to have a three acceptor or three reactive centers. So that's why it is called H3. And the second unit that is attaching, it is having two acid units, so that's it is A2, and the nucleophile is then it is B2. So that's why it is decided. And for this kind of ABC. So what that means is in the monomer itself you have nucleophile and electrophile. So you need not to have two different units or molecule for acceptor donor. You can have this kind of functionality in one molecule. Okay. So for example, here you can see that here two amine groups are there. So NH2 nucleophile, so it is B2, and one acceptor site, it is H. So that's why it is called ABT. So in that way, there are many variants are possible, and with that actually many polymers are made day to day for our day to day use. So in that way you can vary. So here again two acidic center A2 it is B3 and B1, and in that way you can decide this kind of thing. So one of the example is nylon 6,6. So it is a also goes by your step goes polymerization, because here what is happening is two acceptor sites, so it is A2 and two basic or nucleophilic sites of B2. So nylon 60 is a A2B2 type polymerization reaction that we multiple did. And for free radical polymerization, so PVC is very much well known. So PVC goes by for free radical polymerization. And for polystyrene also, mainly radical based polymerization is used. So with the help of a initiator. So with this kind of peroxide bond or peroxide is used with initiator, it generates O dot followed by the C dot, and when C dot is generated, that now can undergo this polymerization. That's how polystyrenes are made. So for this kind of butadiene, when it undergoes polymerization, so there you can expect this kind of branching formation. So when you do this kind of reaction, so it is a here what they have shown, it is a actually radical based polymerization. No, sorry, yes, not radical based, it is a anionic polymerization. So here RL means it is a anion. So now this attack is possible. So now here in the C center, the anion is generated. So this another part now it will do this reaction. And so this is the termination step. But for initiation steps or the chain growth step, so this can again react with another butadiene unit and do this kind of polymerization reaction. So there are actually many possibilities are there, because one for addition is possible in that way, and one to addition sometime also this happens. So when this one to addition happens, here if that anion reacted, so then you can see kind of branch is generated. Now along that line, that your polymer can go. If that kind of one to addition happens, so then you can expect your polymer to have this kind of so there this branching is very much prominent. So along this line, your polymer can grow and ultimately should lead to this kind of structure. So this is the kind of selectivity which things have been have for this kind of anionic or radical based polymerization. So this kind of things actually solved by Piglal-Nata. So if you want linear polymers, then this Piglal-Nata catalyst is very much because that terminates formation of this kind of branching. So in that way, it can be done. Now coming to the carbene. So carbenes also we have some came across in this particular sport. So with variation of your metal that you are going to use, you can have some kind of much more stability compared to this kind of pre-carbene. So if you have and another important thing is so differentiating. these two units, they have some visual representation also. Visually, you can also differentiate between them. So when where it is written, so when your this kind of had been having alkoxy group with a heteroatom, so stabilization, so then that carbon is actually yellowish. So they are actually sp3 carbon. So this case three. When it is a sp3 carbon, you see formation of this kind of yellowish solid, and that represents the sp3 carbon is attached with this particular position. And for sp2 carbons, you would see normally reddish type solids, and they are here you can see it is a sp2 carbon. So that's why it is red in color. And for sp means it's kind of alkynes, you are having this black color. Some kind of dual representation. And features of there we have this reading features class of features of singlets for splits for this kind of stock carbines you are expecting to use or have the metal center having high oxidation state class 5 this titanium tantalum this kind of species. And for feature this kind of chromium based thing are used. Later we can discuss this. Just previously we have discussed this one, so that's why now coming to the metathesis. So it's one of another important aspect that we have covered here was yes, metathesis and this kind of prediction. So for metathesis, so it's the general definition of that. So if A, B, and C, they react with each other, A, C, and B, D. So this kind of partner change, you can this is actually called you metathesis or cross metathesis reaction. So for this kind of alkene, this R1 and R1, this should now react with this or connected with this and this with this. Okay. In that way, this partner exchange can happen and you can have this kind of two products. One of the possibilities. So, and another is this R1 and this R1. So they also can react and ultimately lead to this product that they have. So, the mechanism for that. So, first, that metal carbines that react with one of the uh, alkene group. So, proven one actually. So previously, people thought pairwise mechanism can happen, means uh, two alkenes at a time can interact with this kind of metal units. So this is one of the earlier uh, proposal for this metathesis reaction, but later it is proved that it is not go via this pairwise mechanism. It always goes via this kind of non-pairwise mechanism, means one by one. So one alkene reacts with metals, then followed by another alkene. Not all three reactants react with each other in a single time. So that's proof was proved, and after that, this is the proven or well accepted mechanism now. So at first, one of the alkene unit would come and react with the metal carbines and have this kind of metal fold membrane, and then it would go this kind of ring opening, you can say, in that way. So ethylene is now removed from the system, and this alkene is activated as metal is now attached with this. Now, when This particular carbene is generated metallocarbene. Now this could react with your another alkene that is given, and again you have a four member metallo ring formation and followed by this, which leads to formation that of your cross metathesis product, and obviously it's also going to regenerate your catalyst, and that can undergo the next or further cycle for this catalyst. So the the for catalyst for carbines. So for that, this molybdenum, this kind of metals are used, with presence of this kind of ligand. And for grubs one, so they are generally ruthenium based like this. So initially they have prepared this with this kind of cyclopropene ring, and with ruthenium based this reagent, it reacts with this cyclopropene, and this opens up and ultimately leads to this point. So now if you see, this is nothing but that initial catalyst of ground in 1992. Now followed by these, they have reacted with different azo compounds, and that leads to this formation of this kind of metallocarbene, and with uh, lithium medium. So what they have done that they just replaced this ligand. So PPH3 was replaced by PCY3 cyclohexane. So this particular structure. So initially PPH3 was there, and with this thing they replaced that PPH3 with this PCY3, and that leads to this particular compound, and which is nothing but your first generation graph catalyst. Now for second generation, so this is actually reacted with this NAC, in cyclic carbene. So this is reacted with this kind of ligand. Now this can actually the nitrogen is here. Now this is actually the initial starting material. Now if it is reacted with potassium tert-butoxide, so this kind of bases are used. So this would take this particular proton, they are acidic proton, and generate minus, and ultimately they balance each other, and here you have that carbene. So that's the way to generate this NAC, and that would replace one of the PCY3 ligands and lead to formation of Crab's second generation catalyst. And it's the other thing. So not only PPA3, you have this kind of variant. So on the same line, you can make this also, and with this NHC, you can replace that PCY3, how the second generation was made. So a similar way, you can make that this catalyst one. So that's the regarding this metal carbon chemistry. Now after that, we have read about that sandwich molecules. So these are the different kind of sandwich molecules that we have came across in this code. So this is half sandwich, or piano stool, which is also known as piano stool. So on the one side it is having that cyclopropene ring, and another side no cyclopropene or aromatic ring is there. They are sort of ligands are present. So that's why they are called half sandwich molecule. And this is the well-known metallocene. So sandwich molecules both sides cyclopropene ring in that way. So this is the one of the major variants in this family. And for bent metallocene, so this kind of metals now have this kind of two different other ligands. So four ligands are there, two cyclopropane and two another ligands. So where another two ligands are present, this bond obviously should be kind of bent. So that's why they are called bent metallocene. So this is one of the other, and it is called actually bimetallic half sandwich. So now if two half sandwich molecules make a dimer, this kind of metal bond is formed. So then you can expect to having this kind of structure. Now it is called as your bimetallic half sandwich. Now another this kind of variants are also there. So they are rare, but obviously they are present. So multi-decker compounds means not two. There are many, three, four, this kind of different decks. So that's why it's called multi-decker. And again, these kind of compounds are also there where this cyclohexane is attached with one common unit and kind of pain metallocene. But so uh, is one of the example like this. So these two cyclohexane ring are attached by a common connector, and that's why this particular this bond ending is there. So this is another example. Now, if we look into the most of that, so for metallocene, so these are the possibilities we can say for your cyclopentene. So here these five lobes are possible. So for this case, it is having no there is no node or nodal plane. It is A1 like this. Now these two compounds have, or these two structures have two nodal planes. Sorry, two nodal points, one nodal plane. So this one and this. So one nodal, so two nodal points and one nodal plane in that way. Now for this case, you are having one this nodal plane and the similar line. Differentiating between them, the nodal planes, the energy we can decide, and they separate from that with A1, U1, or U2. So according to that, it is decided. Now they are actually energy are same, so they are W degenerate, again E2 W degenerate, and they are similarly degenerate. So that in that way, the splitting pattern you can use for this kind of cases. Now, when we have you have this sandwich molecules, so two cyclo propene rings are there now. So for this kind of cases, you can expect to have this kind of pairs, and according to the geometry and uh, uh, that nodal planes kind of deviation you can expect, and these are the available options. This is the thing we are talking about. So here's no nodal plane, here one nodal plane, one nodal plane. So doubly degenerate, and here two nodal planes, four nodal points. So again, doubly degenerate. So that's why they are actually decided. Now coming to that interaction, how it happens between your metal and cyclo uh, uh, protein cyclophane rings uh, this particular ligand system, they now react with your metal. So that what that sandwich molecules. Now, if we look into the orbital interaction, so it's the d orbital. So we all know. So the X Z is uh, remaining this kind of axis, and the Y Z X Y X Y minus Y square and Z square. So well-known d orbitals, and these are the p's and s orbitals. Now, if we see the interaction between their, I remember types law of Penrose's two experiments. So, that ring and your metal, here you can see that the interaction that are going to be present. So for so this is what you have. It is A1, E1, and E2. So according to this line, we are explaining. So it is A1, E1, and E2. Now, that pictorial that they have shown is from the above side. If we see, so that will be easier to understand. So now for this case, here you can see is comparing different d orbitals for dz square. You can expect this kind of symmetry matching because this square is aligned with this the coordinate, and it can have this kind of interaction. So is A1 or dz square, your dz square obviously is going to be yeah, close due to that symmetry matching. So that's the interaction with A1. Now, if you see that E1 case, so for that the YZ can be used because for DZ here we have this kind of arrangement of orbitals. Now, if you use DZ, you can have this kind of bonding interactions. So that's why DZ can be used for this particular arrangement. And for E1, DX that can be used. So the same reason that symmetry matching and orbital interactions. And for each cases, so the x square minus y square and the x square is so in that way you can decide again bonding interaction. So that's the way to decide. So it's the full Phillips scenario that you can expect. So here all are here you can say they are actually dark. So now they can react with your s orbital fully symmetric. S orbital can do that, and another is the jet stream. So these two can react with your A1. For A1U, so uh, for A1U, it is kind of like this. For the one, so half sandwich molecule, you can consider this. So now it's the full sandwich molecule. So for A1U, you have this kind of arrangement. So now for interaction to happen, you need uh, kind of TJs because this dark combination followed by light. This is important, and TZ can maintain that, so that's the reason. Symmetry matching is the key to assign each orbital would react to each. So that's the way to decide this. So here TZ is real. Now if you consider E1G, so here I can do this. So here each one have this interaction now. This and this can interact in the same way. The but bottom line. So the bottom the arrangement what they have given is it is kind of way the same way actually you can do. So it seems that it can so so if you see here it will be easier actually to understand. But it is the E1G and it is the set. Now if it comes like this, so here you can see that this dark portion and this so they react, and the light ones are also matched. And for this case, it is in the middle, so this light they are here and dark is there. So that's how that um, matching is there, and you can do this kind of interaction. Right. And for PX, sorry, for E1U, you can use the PX orbitals. So the reason is there, so where that orbital matching is there, you can use that particular um, arrangement. Now for another E1U, you can also use this EY. So again, this light and light. So this kind of interaction would be there and followed by the dark. So the same thing, and for DYZ, they would again going to react with your U1s. And for ultimately that A1Z, so this one we have seen and everything. So all are now covered. So now the classification of the bonds if we see. So here you can see kind of head-on interaction is there like this. So that's why it is called a sigma bond. So this kind of interactions that leads to sigma bond. So that's why these are called sigma. And for this case of they are called pi bonds. So for pi, what we have seen, two orbital or this kind of four, this kind of interaction is there, and which is equivalent here. We are just seeing this kind of interaction only. So that's why they are known as pi bonds. And for here, so there's special one, so delta. So for delta studies are having at the time this three orbital thing interaction, and they are known as um, delta bonds. Now, after doing all the correlation, now coming to the final image, what we have matched over here compared to your symmetry and all, but so it is easier if you have assigned this U1 if and comparing that you can just do that interaction. So here U1 and E2 they interact with this U1 A2 or U1 U1. This interaction is there, and they're obviously going to form this bonding anti-bonding thing, and all the possibilities that we have just discussed we can just plot it over here, and ultimately it will lead to this kind of emo. So the general emo we can solve for this kind of sandwich molecules. Now the important thing is this five orbitals, and according to that you can assign your metal electrons, and with that you can decide it. So the orbitals we are going to be mainly talking about, because anyway these 10 electrons are going to be filled by these A1, A2, E1G and E1U. So with that it is filled to 10, 1, 2, 3, 4, 5, 1, 4, 5, 6, 7, 8, 9. So they are covered. Now, these things, so this if you see, E1G and E1G stuff. So that is remained, and the metal electrons they are going to be filled here. Now, metal obviously we are going to vary from iron to copper to nickel, and that would be actually mainly different. And with that, we can decide that different properties. So these five orbitals we should always remember, and here actually that main thing would happen. So for vanadium CP2, so it is having three electrons, so it is going to be arranged like this. For chromium, you can expect this. For manganese, five high spin. So this kind of arrangement. Now when you CP7 means they are low spin. So for that only it will be paired. So now iron six would be paired like this, cobalt again paired, one unpaired electron would be there. And these are the variants actually, another no issue. And with this particular orbital setting, we can explain their property. So, for titanium and molybdenum, so mainly bent metallurgy we can see. So, this repeating, this you can see that uh, this particular five orbitals are mainly focused for this because anyway the other that this particular portion are going to be filled by your this five membered electron. So the one now this d5 and this are going to interact and have this kind of MO, and accordingly you can do that arrangement. And for this again, the same thing that is we can do this kind of arrangement and decide that here you can see that field orbital or non-bonding orbital release gas non-bonding electrons in that. So this is we have just seen that metallocene. Now another thing we have covered was this kind of metal monohydride complexes. So if you see different properties of this, yeah. So initially we have read out this kind of photo processing. So metal hydride this hemolysis is one of them. So when it is reacted or such with this kind of light, you can expect formation of this H dot, and not only that, this particular RJ also can be broken. So it's kind of reductive elimination of this metal low, so non-metal normal alkanes. And another thing is dissociation of L means that one of the ligand can also be removed from that metal. So this is one of the possibilities because the isomerization is very much feasible for this kind of cases. So thing to trans this thing is again possible. Another thing is MLCT. So proton transfer and hydrogen transfer. They are also accessible. So with tungsten based hydride, this observed actually and with this kind of epoxide at first it is attached and which is attached to pure bond is broken with hydride and this is the example. So these are examples of different reactivities of this particular compound. So when it is reacted with ethanol, one of the hydride is removed and OM is replaced that with the normal benzene. We also can do this cage functionalization like this for acetylene, so that's for toluene also. This kind of things are there. So when nucleophiles are used, what we are seeing that formation of hydrogen and the nucleophile is incorporating in functional function. And with this kind of uh, what we have initially talked about that bimetallic half sandwich kind of molecule, so that also can be formed for this tungsten. So with ether, this kind of bimetallic complexes can be formed. Now for this kind of units here, again, you are seeing that but it is kind of reacting like what it reacted with this kind of that kind of sorry, epoxide. So it's inserted between this carbon oxygen bond and in similar fashion here you can see it inserted between this carbon and sulfur bond. So it's the same kind of reactivity it can react. And obviously other possibilities are like this and this can be uh, coming to this quartz reagent. So these um, formed on this PTR with this zirconium fluoride salt in presence of lithium aluminum hydride, and you can have this kind of results. So these are the reactivities of this particular reagent. So they are quite useful So they can be reacted with this kind of amides and this formation of this aldehyde molecule. So amides to aldehydes, for that case, this zirconium based reagent can be used. So not only that amides, so they also have different reactivities. If you have this kind of alkyne, so again, for this you can use it with this particular reagent, and so that ultimately what you are generating is that uh, this particular carbon is reacted like this with tongue, and here they can act as nucleophile. You can vary the electrophile. So here they have used iodine. So that's how that vinyl iodo compound can be used. In the similar way, so here, not tungsten, zirconium is used. So for this case, the electrophile they have varied and they have used this particular uh, mean type of compound. So for this, it reacts this one to addition in that way, and it is actually chiral version because that the feeding or airing that is used was this particular ligand. So with this selectivity or enantiomer express, you can put this. So again, this is an example of amines to this particular compound. So we have different activities. We have shown already. So vinyl to this alcohol again, the same it can react. California would activate this double bond, and this is reactive that aldehyde. And uh, so different activities are there, and when this is one of the yes, example you can see. So with zirconium based reagent in benzene, at first we have this particular reactive intermediate. Now it's having different reactive profiles. So with HCl, it is H plus. Here you have normal alkane. So you have bromine, which is electrophilic unit. So you have this bromo compound, and then you have this uh, fluoro compound or acyl chloride, and this acyl group. So the same way, kind of thing, uh, it can be used again. So another example. So if you have this intermediate without quenching here, you can use carbon monoxide and then one carbonyl insertion reaction and followed by your this boronate. You can do this particular cross coupling kind of thing. It's one of the yes, this palladium is used over here. So cross coupling also can be performed with this zirconium based reagent. So this particular nut we have read already stochastic and how they varied and how that variation can be done. So that we have already discussed. And here actually another thing is the difference between this Ziegler and Netta were the use of different CICLs. So there are this kind of alpha, delta, gamma, this kind of uh, uh, PICL3 are available. So how they this thing is given? So they are mainly that. crystalline phase or in crystal how they are arranged. So according to that, these particular variants are there. So for beta TLCL3, it is actually brown in color, and NASA actually used this particular beta TLCL3. And Cigarette used that HTL4. So uh, they are kind of difference is there. So when you use this brown kind of PICL3, there you can see improvement in seriously activity. And when you use this violet color means alpha, delta, or gamma, then dramatic increase in stereo selectivity is there. So the difference of kind of CICLC also, this kind of thing can be expected. So these are the actually something how with aluminum that activation happens and this active side is formed in titanium. So this we discussed that one hydrogen side and at first is reacted and then flipping kind of thing. So this is the structure of alpha TiCl3 and for this kind of cases, if you see two enantiomer catalytic cases are there, so that's why that stereotactic polymers that you are going to be forming and the mechanism, different proposals are there. So here, after migratory insertion, here you can see that black strip is happening for this, so that's why that stereotacticity is maintained and for this beta. So, this is actually your the activities of not the activity, but serious selectivity. So alpha, delta, and gamma, they are violet and highly selective, serious selective. And from that, your beta T ICL3. Beta T ICL3, your selectivity is very much lower. So for beta CL3, half of the Ki atoms have two backs side. And for another means other variants of titanium atom have one button. So that's the difference, and that can be explained from this particular crystal structure only. And according to that, these variations are there. Now coming to that vanadium and this. So why for this system it is similar tactics, and for titanium it is uh, for titanium it was isotactic. So for titanium it was isotactic and for vanadium it is singular tactic. So the reason is for titanium here we are seeing a back flip that is happening here. So that's why this particular physiochemistry is maintained. And for vanadium, what is seen that this backflip that is very much visible in titanium that is not possible in vanadium. So that's why no backflip and that would ultimately lead to this thin diatactic minerals. So another thing we have learned is this one, uh, so how that this kind of polymers, plastic can become conductive. So plastics are actually polymers, so long chains are there, and if you want to make them electric or conductive, you need to have something um, that can control the flow of electrons from one end to another. So for metals, because three electrons are there, so that's why they are very much conductive. But when comes to this kind of organic molecules, so this kind of electron transfer from one position to another position is very much easy or not possible only. So that's why generally these plastics are not conductive. So it's one of the Nobel prizes that people have received in 2000. How the plastic can behave as conductive. So for that polymerization, this kind of polyacetylene molecule. So not alkyl. If alkynes were used for polymerization, so then you can expect formation of this kind of polymers where double bonds are there. So now you are seeing so this kind of conjugation is always there. So that's the way to make one flow, this flow of electron from one end to another end. So using this particular possibilities, these people have worked and they have used polarons or doped carbon chain. So what they have done is they have used some kind of oxidation reactions like iodine they have given and taken up one of the electrons. So when iodine is taken and it acts as oxidant, so electron is transferred to iodine and it makes I3 minus. So in this kind of way, the surface is charged as negatively charged, so I3 minus. Now this polyacetyl molecule is now positively charged, and this thing only is termed as pure radical cation or polaron. So after reacting with iodine, here you have general. So here you can see that one of the electron is transferred followed by next one. So in that way now your chain is positively charged and that can move from one end to another because you have that conjugation. So in that way, they have designed this and make this kind of conductor. This is one of the examples. So then we have uh, in this kind of processes, SHOP cells higher olefin processes. So there this kind of rich acids and molybdenum oxides are used and sort of coupling products are there. So they are actually skin transfer. So when you make larger polymeric units, so these reagents can be used and it can do this kind of cross metathesis and can have different values. So this is one of the examples. So hydroformylation is one of the so from here with cobalt reagents reaction followed by reduction. With that, you can have this kind of alcohol with very much big uh, polymeric chain. So for fatty alcohols, this kind of process are used. So lastly, I would just want to discuss that carbines, and we can come up. So if we are actually so first off, so just in the last class we have just learned. So the presentation we have seen now, the mixing process. So with methyl lithium and this kind of carbonyl unit is to react it at first generate this kind of unit and followed by diazomethane unit is reacted. So this minus now it reacts over here and you can have this methyl. Here you can see this kind of a means not this methyl. This O minus is reacting with this and you are having this anything. So it's different representations with tungsten, chromium, iron, manganese, cobalt. So kind of lower valent or lower oxidation states in 2 plus, 3 plus mainly, only 2 plus oxidation state. And so this is the you can say is that orbital interactions. So it is singlet carbene. So for this kind of case, what happens is field, this one is field, and with empty the orbital it reacted like this, and ultimately it's a fissure, and that backwardation is obviously possible. Pi and sigma, this kind of interaction is there, And for shock, so this radical based thing you can consider as the triplets. So this dot would react with this dot and this kind of interaction. And, and the examples and the way how kind of Fisher and carbon react. For Fisher, it is electrophilic position, and for Clock, it is the nucleophilic position. Reason being, it is a highly oxidation state plus 5 plus 4. So that's why this carbon is negatively charged and this express nucleophile. And for this case, it is different because metal to carbon, this transfer happens. So it is reverse. So here it is a electrophilic sensor and this thing is happen. And here you can see the tungsten is zero oxidation state. So that's why this in that way reactivity is short. Now these are two options, so it can also react with electrophile or nucleophile, and ultimately this kind of thing. So it's fine, and it is another way to make carbines. So not only with this kind of methyl lithium, with this kind of patterns also you can make it. So if you have this particular compound and it is reacted with this, so at first this kind of interaction would be you can have. Now this position O minus can react with your acyl group and do this thing and ultimately leads to this. And then you can obviously use one of the alcohol. So if alcohol is used, so this whole part is reacted or use can be used as sleeping group, and this kind of carbons can be made. So with another way, so with see this potassium at first you're going to have this one of the carbonyl or carbon monoxide is leaving from that metal, and you have this. So it is a 2 minus. So this metal when reacts now with acyl group like this, and along the same line, the previous slide. So in the same way, we can make this kind of compound. Another way is directly if you want to incorporate this nitrogen. So that also can be done. So here you can use amide. If you use amide over here, these things can be happening, and with PMSGS, this elimination is possible. So for that, kind of variation is obviously there. This is another way, obviously, if you have OME, so that also can be removed or swapped with this kind of primary amines or secondary amines in that way, then you can have this particular compound. And for this, in the same way, actually, this interaction and this interaction will ultimately lead to formation of this fixed membrane, and they are actually swappable. We have actually ended up with carbon chemistry, and in that way, different nucleocarbons can be. So, these are the actually today I can stop over here. So today I just want to give you just brief overview of what we have actually covered. So initially, we just looking into it. So initially, Ziplanata for that linear cell formation that can be done, and that would lead to two symbiotic or isotactic. So differentiating titanium to vanadium, that two things can be regulated. Now it comes to characterization. So with in image technique we can do that. So the formula is like this. So with this actually we can calculate the number of substitution units with the institution and then decide that. Then tax history we have seen when all are kind of in the tax. So method ads are there, and when it is this kind of way, so destiny ads are there. So they need to search in their technique, and then that is isotonic. And when there is no such order is present in your system, it is attached. After that, it is actually why it is important actually because it ultimately leads to different properties of your material you can say because ultimately this structure varies and that actually dictates how your molecule would behave. So that's the reason toxicity is important. Now after that we have read shape polymerization. So it's generally this kind of condensation reaction are known and there are different types compared to your acceptor and donor side. We can call it as H2B2, HTBC. So we're comparing with the number of acceptor units that are present. We can decide that. So it's some of the examples and why the branching happens for anionic and cationic and radical the same way you can think of. So initially they are actually popular. So after that actually Visual Nataka and they are actually people are able to make that linear or linear kind of way without having any branch. So that's one of the key modifications. So then the carbines we have red and just we have discussed carbines. After that we have this the metathesis reaction. So again this particular carbene line actually so metal carbene they are actually used for this kind of metathesis reaction. So the partner exchange you can say AABC is this kind of thing. So cross metathesis. So for example, so initially pairwise mechanism or so forth, then modification or now this proven now it does not go via this paired wise, it is unpaired wise mechanism and this is the mechanism of that. So one unit would react with one alpha followed by another. In that way, it would go through. Then cross catalyst for this kind of metathesis reaction, and this is perhaps one, and the way the filtration happens, and convention and then this kind of modifications. Then we had discussed this different type of sandwich molecules. So have sandwich, tea sandwich, this kind of things. And some MO diagram we have explored it well. So compared to that orbital symmetry machine, and it's the MO of ferrocene. And after that, different kind of metal reagents and aggressive effects kind of thing. Zirconium, tungsten, we have discussed and followed by different processes. Uh, that's best flip one and there is no best flip for vanadium. Then this conductive polymers and followed by this process. So that's the actually whole overview what we have done in past 8 weeks, 8 weeks, 8 lectures. So that's the whole story. Sum up we can say. So now, if you have any question now, you can ask. It seems like no questions, but that in the portal itself, the doubt clearing the section is just if you have any questions, how you write there, you can do that also. So I would answer there. So that obviously can be done. So for the lecture series, I think we can end, and I hope all of you enjoyed this course. And obviously, if you have any question, you can mail me or in the portal itself it can be done. So we can thank you all for staying and attending all the classes and all the best for your exam. So thank you.